Hello, welcome to this free training session, getting started with IDEA StatiCa. Topics for today is, first of all, steel, the connection library, the BIM links, and then concrete. So let's start with steel. First of all, the connection application. We can easily deal with the standard connections. There are, of course, design guides and predefined examples, but for the non-standard ones, we usually need to put together a advanced scientific model in programs like ANSYS or Nastran or Abacus, then use Excel spreadsheets to get the code checks and estimate a lot of variables on the way. Sometimes it's just easier to avoid such a joint. So this is where IDEA StatiCa comes in to help you to deal with both the standard connections and the complex ones. The different types of analysis you can do in IDEA StatiCa is, first of all, the stress-strain analysis. This is where you get your, of course, the stresses, the strains, and you do the cold check of the connection. You can also do buckling analysis, stiffness analysis to classify the connection, even if it's rigid, semi-rigid, or pinned. You can also retrieve the rotational stiffness of the connection. Then you can do fire analysis, capacity design for the seismic connections, where you can insert plastic hinge. Then you have the design joint resistance, where you can retrieve the reserve capacity above the load you have already applied to the connection. And then you can do fatigue analysis and horizontal tying checks. So all types of connections are possible to check in IDEA StatiCa. The method on which the steel part of the software is based upon is the CBFEM method. So it stands for Component-Based Finite Element Method. And this method is based on the idea that most of the verified and very useful parts of the component method should be kept. The weak point of the component method is generally when analyzing stressed or individual components was replaced by modeling and analysis using the finite element method. This means it is a unique method for design and code check of steel connections, members, and anchoring. It can be used for the majority of joints, anchorings, and details of various topology. Before the analysis starts, the connection CBFEM model is automatically generated. It consists of plates, bolts, anchors, and welds. All plates are meshed with shell elements. Bolts and anchors are represented by special nonlinear springs, and welds are discretized and modeled as special constraints, enabling the stress distribution due to their plastification. And if you're interested in going into the theory more in detail, you will also find it in the theoretical background on IDEA StatiCa's website under the support center. Here you'll find theoretical background. You have the general theoretical background going through all of the setups for the software. And then you have the more specific one, the check of steel components according to Eurocode. Let's take a run through the connection application. First of all, you are presented with some templates. There are 250 templates with different topologies and different types of connections. You have footings and more complex connections. For this demonstration, I will open one of the connections, for example this one. And this is a perfect start-off point where you can then choose something that looks like the connection you are designing, and you can continue with this. So you can choose the default steel grade, the default bolt assembly, weld grade, concrete grade, and you can also choose the code you are working with. We will stick with Eurocode for this demonstration, and we will create the project. Here we have the connection, and right now I'm not going to do any changes. But if we have a look at the connection itself, we can inspect it, and we can see the members. We have two members, we have a load effect, and we have some loads on each end of the members, and then we have the operation. So in this case, we have a end plate with some bolts and welds. If I deactivate the stiffeners, it's much more clear. If I deactivate it, we can see that we have just the members. I will activate it again, and we can take a look at the menus here before we run the code check. So first of all, I go back to the project tab. This is where you can put in some information about the project, for example, some names, author, and description of the project. In this tab, you can input text or pictures for stuff that you want to include in your report later. Could be a reference to where in the model this connection is located, and so on. In the preferences, you have the ability to change the company logo and all sorts of different settings. So I will go back to the design window. This is where we do the design and modeling and apply the loads for this connection. We can have a quick look at the menus. So in the labels, this is where you can turn on the naming of the members, the plates, or the local coordinate systems for the members. You also have a picture function where you can take screenshots, so to say, in the program, and you can have it included in the report later on. The connection library, we will go through that later. And then you have the code setup. In the code setup, you can then input all of the factors, the coefficients from the national annex, or if there are some special considerations that you need to take for your connection. Here you can then input the safety factors or possibly some friction coefficients and so on. All of the plates, the shell elements, is checked for plastic strains, and the limit is 5% according to Eurocode. And you can set it here if you want to have the limit plastic strain lower. Here you can also do some fine-tuning of the mesh, even though the mesh is calibrated to suit almost all connections. But here you have the possibility to do that. The calculate button, this is when we run the code check. Then we have the settings. Here you can have some estimation of the cost. If we input some currency and then go to the steel parts and input the price of the steel, and same for the welds, the bolts, drilling of holes and stuff like this. In the design button here, you can then choose if you want to have some auto design. There are functions for limiting the utilization, for example, for welds and bolts. And then you have the fire design when you have to do a fire design analysis. Here you can input the fire resistance class and so on. Then you have the loads in equilibrium. We will go through that in a moment. Basically means that the connection has to be in equilibrium. The internal forces has to be applied in the correct way so that the connection is in equilibrium. You can also import loads either from Excel or from your global analysis software, your FEA software. Then you can use this button, connection import. I will show you that later in the BIM link section. Here we can also export footings to the detail application, and you can also export the connection in the IFC format. Further on, this is where we can add new members, load effects, and of course the operations. If you are manually modeling this connection, we can then insert cuts, stiffeners, openings, welds, bolts, plates, stiffening members, and so on. There are even working planes, negative volumes, and lateral torsional restraint if you want to use some of these operations. On the right side here, we have parameters for each operation. So in this case, we have the stiffener highlighted, and we can now, for example, choose to remove the chamfered corners, or we can put in a repeat count, and we can choose to move the position of the stiffeners, and so on. If we are happy with the connection, we can run the code check. So I hit calculate, and we get a summary of the code check. We also get an overall check of the connection. It's color-coded to show the utilization of the different parts. If it's gray, it's between 0 and 60% utilized. If it's green, it's between 60 and 95%. If it's orange, then it's between 95 and 100%. And if it's above 100%, the part will be red. In this case, we are good. We have green check marks, and this summary shows that all of the loads were applied successfully, 100%. Here we can see the plastic strains of the shell elements. In this case, we have 0. And then we have the utilization of the most critical bolt and weld. So we can move on to the Check tab and look at the results in detail. First of all, I can visually inspect it by turning on the strain check and then looking at the stresses. To make it even easier to see, I will turn on the mesh and the deformed shape and check if the connection is behaving as expected. In this case, it does, and we can then move on to check the results more in detail. So we have a tab for plates. Each and every plate will be represented in this table, and you will get a plot of the plate. We can move on to the bolts. Here also the bolts, all of the bolts are represented. We can see the naming, the critical load effects. Here I only have one load, so it's load effect 1. We also have the tension force, the shear force, and then the utilization in tension and shear and so on. We can expand this menu to review the code check, and we even have the reference to the Eurocode, and each and every check is represented here, depending on how the bolt is loaded and what kind of bolt it is. Same goes for the weld. Each weld is represented in this table. So here we have the thickness, the length of the weld, the critical load effects, the stresses, the strains, and so on. And you also have the utilization of the weld. I will go into detail a little bit later about the welds, because you have 2 different kinds of utilization factors, but we will look at that later. So if you are happy with the connection, we can then go to the report, and we will generate the report. So here we have a default kind of medium detailed report. You have the possibility to change the type of report. You can have a brief report, a one-page report, or this detailed report as we have now. The basics, you have some project information, you have the geometry and the members and the support of the members. Then you have the different cross-sections and materials, the bolts, the loads applied to the connection. And then you have a summary of the code check with OK or not OK. And then the plates and some plots with the stresses and strains. And then we have the code check of the bolts and the welds. And at last we have the code settings. So the safety factors and the coefficients and so on. It is possible to expand this report if you want to have more information included. Then you click these tiles on the right side, and you can generate a new report. Here we have it. Now we basically have the same results, but it is expanded to include every code check of every bolt, every weld. You can find it here. And then you have a bill of materials and all of the plates with measurements. So this can be nice to have included in the report. The report, you can export it to a Word document or a PDF and continue to edit in Word document, for example. So the last tab is the Materials tab. This is where you can have a look at the cross sections, the characteristics, also the materials. You can make your own material if you have some special material that is not in the library. The same goes for the bolts. You can even have pins also. If you cannot find the cross-section in the library, you can of course make your own. Then you can go into the cross-section editor, first of all the library, and then go to Welded Composed, and then you will find this cross-section editor. And this is where you can choose a cross-section to start off with, or you can simply import a DXF drawing, and then you can continue to edit. For example, here I just make like a star-shaped column type of cross-section, and I can use this in my connection. So that was a quick run through the connection application. So now you have seen the demonstration of the connection application and the workflow of how to work through the steps. Now I want to show you a couple of things that you need to keep in mind before using the software. First of all, some definitions. The main members you can apply load to. They are defined as members. You can even have them ended or continuous. If you want to connect two members together with some stub or for example, something like this, you have to apply a manufacturing operation called stiffening member. You cannot apply load to it, and this would be the best way to have a stiffening member like this. Also, about the node, you can only have one node for each connection. And if you are in doubt, if you have some eccentric beams coming into the connection, there might be a question, is this one connection or is it two connections? There is a good webinar going through exactly that topic on the IDEA StatiCa website, so have a look at that. One node, remember that. I touched on the loads in equilibrium when going through the software. Basically, it means that you have to input all the internal forces for all the members in the connection. It must be in balance by the law of statics, and this is a much more safer approach. So this button, loads in equilibrium, it is on by default, and you can get a table showing the unbalanced forces if you have unbalanced forces. But basically this should be 0 or close to 0. There is one exception, and that is footings or anchorings. You can of course not get equilibrium. This is where you input the forces in the load effects. You can input the forces for each member, and then you will simultaneously see the unbalanced forces when you input it. But if you use a BIM link, that problem is solved. Then all of the internal forces will get applied to the correct members automatically, and you are good, and there should be no unbalanced forces. And then you have the possibility to change the model type. This is to select what forces can be applied to the member, so other degrees of freedom are restricted. By default, you have the general type where all of the forces can be applied to the member. But in special cases, you can restrict some degrees of freedom. The most common type is the one-bolt connection. Here you have to choose the NVY-V set. This is an example where you have a one-bolt connection. If you choose the model type with no restrictions, then you will get deformation that is not realistic, and you can see that the member is rotating. There is now a mechanism, and the analysis will probably not finish and it will cancel. The correct way is to set the model type to NVY-V set. Now it's only taking normal force and shear force, and the results will be trustworthy in this case. You also have the possibility to change the position of forces. So you can choose between node, bolts, position, and finally member faces. So let's go into this. Basically, the real shape of the joint looks like this, but the theoretical shape looks like this. We can see that there is a difference in the distance between the real shape and the theoretical shape from the connection itself. If you have a rigid connection, you simply don't have to worry too much about this. The moment and shear force diagram will look like this. But if you have a hinge, the 0 point, the point where the moment from the shear force is 0, is in here. If we look at the real shape of the joint, we will then end up with moment in the hinge itself. This will give unrealistic deformation and results that are not trustworthy. So the developers has made it possible to change the position of the forces to some x distance from the node. And in this case, where we have the hinge out here, we will have to change the position of force x distance. In the program, you have the forces in. By default, it's set to node. Then it will look like this. But if you change it to bolts, the point of the 0 moment will be in the position of the hinge. And this is the correct way to do it when you have a hinged connection with possibly only shear force applied to it. The consequences, if you have the node, in this case, the deformation will be like this, even though the shear force is pointing down in the gravity direction. But if you input the correct settings, so the bolts, the deformations and the results will be realistic. Then a couple of words about welds. In the result tab for welds, there are 2 utilization ratio listed. The UT shows the utilization value of the most stressed finite element of the whole weld, so the peak value, while the UTC shows the utilization of the whole weld and thus gives the user information about the remaining weld capacity. Since stress distribution in welds in FEM-based models varies based on applied loads, it is not simple to determine the remaining capacity as a linear function. With the increment of applied loads, the change in weld stress distribution can be very dramatic. So let's have a look at this weld. When we run the code check, in the summary we can see that welds is utilized with 98.2%, but that is not the case always. If we go into the check tab and the results and look at welds, we can go to the UT, utilization of the most stressed element, and see that it is 98% for sure. But if you go to the UTC, so the overall estimated utilization of the weld, we can see that it is actually 62.2%. And the picture is more clear if you go down to the equivalent stress along the weld. We can see each element of the weld is represented here. And in the middle, we have some peaks. And if we look closer on this plot here, we can see that the peak value is 427 megapascal and the limit is 435. And if we divide it, we get to 98.2%. And a simple calculation of the UTC, so the overall capacity of the weld, it's the A1 area divided by the A total area. And then we arrive at 62%. But that is a simplification. The actual calculation of the UTC uses a machine learning estimation function. It's based on learning from a vast number of welded connections and various load scenarios, and this algorithm can accurately predict the remaining weld capacity. This functionality is the first successful use of AI and machine learning to determine the capacity of welds. And yeah, the best thing about it is that the application can do it within a 10% threshold. So keep that in mind when looking at the weld results. So let's look at the next topic, which is BIM Links. This is how you connect IDEA StatiCa to the software that you already have. So the CHECKBOT is basically the BIM link. This is a plugin or add-in that you install with your already existing softwares, so your CAD or your FEA software. And basically you can import loads and add design if you go for this FEA software route to IDEA StatiCa. Or if you only will use the CAD software, you can import the design and then add the loads in IDEA StatiCa. You can also combine the FEA and the CAD software import possibility, which I will show you the workflow. Here are the different softwares that are linked to IDEA StatiCa. In the CAD category, you have Tekla Structures and Revit. They are the most common ones. And in the FEA software, you of course have the StadPro, the ETABS, R5, SAP 2000, Robot, and of course FEM-Design. This is the workflow of how it works. If you combine it, you can then take the geometry from Tekla or Revit, put it into IDEA StatiCa, and then you import the internal forces from your FEA software and apply it to the connection that you imported from Tekla or Revit. If you do not have the Tekla or Revit model, you can of course work with only your FEA software and then import the connection, including the internal forces, into IDEA StatiCa. And then you have to model the connection or use something called the connection library to finish the connection. Here we have a Tekla model. It is completed with all of the bolts, welds, plates. I need to just check if the connections, if they are okay. So I have to code check them. I also have my global analysis model in SAP 2000. The procedure is basically the same for all of the softwares when you do the import or export. So I will use SAP 2000 in this case. I will start with the Tekla import to the CHECKBOT. So I will run the BIM Link CHECKBOT. It is automatically installed when you install IDEA StatiCa. Here I can then create a new project. And now I have the possibility to import one connection at a time or a bulk selection. I will do the bulk selection and I will simply mark the connections I want to import and hit space. I can choose to also import recommended welds, but in my Tekla model I have already applied some welds, so I will stick with them. Here I have the structure. I can start to look at this connection down here. So I'll open it in the connection application. Right here you will not see the plates, bolts and welds, but we will see them once we open it in the connection application. So here we have it. We can see that the beams, the column, the plates, bolts and welds are imported correctly. And the only thing I'm missing now to run the code check is the loads. So let's go to the global model, the SAP 2000, and we will do the same thing here. First of all, I have to run the analysis to get the response. And now I can then simply start the add-in, IDEA StatiCa CHECKBOT. And from here, I have to run the almost the same procedure. In this case, I have to first mark the connections, so the same 4 connections. Go back to the CHECKBOT and hit import connections. So now it will import the beams, the columns, and the loads, or so to say, the internal forces applied to the connections. In this case, I have to do some small modifications. The column and this end beam, it's supposed to be continuous. So I will mark the column, hit merge, and I will merge the column first, and then this beam, like so. And now these 4 files are stored in the folder under the SAP 2000 project, and they contain now the information about all of the loads on all of the connections. So what I can do now is jump back to the connection that I imported from Tekla. and I can hit this connection import button. And now I must find the correct folder where my SAP 2000 project is stored. Here we have it. And it is this one, the first one. I will open it. And then all of the loads, the internal forces, are applied correctly. Just a quick note on the applied loads. They are actually internal forces acting on the node. So if I switch to this wireframe view, we can see how the loads actually is applied to this connection. But if I switch to the solid view, we can see the condensed super elements, and the loads is set on the ends of the elements or the members. I can see that I have my ULS 1, 2, 3, so my 3 load combinations, they are there. And this is a pinned connection with only shear acting on it, so we have to remember to change the position of the forces to bolts. We can inspect it if we just switch to the transparent view and then mark the member. I can see now that the point of the 0 moment is in the middle of the hinge, like so. If I switch it back to the node, then the position of force is the 0 is in the node, but we now have a moment in the hinge. So I will do it the correct way, choose bolts, and the results will be trustworthy. So now I'm ready to do the code check. I will hit calculate, and the program will apply the loads, all of the load combinations, and do the code check. And we are done, and here is the summary of the code check. We can see that we have green check marks, and we are good to go. So I can save the connection, exit the application, and if I go to the CHECKBOT, I can now move on to the next connection and run through the most critical connections, or every connection if that is what you choose to do. This is how you combine your CAD software and your FEA software. But let's say that you only have the global analysis model. In the case that I only had my SAP 2000 model, I will export it to SAP 2000, and I can simply open the connection from here. So if I do that, we can now see that I only get the column, the beams, and the internal forces. But I do not get the bolts, the welds, the cuts, and so on, because this is straight from the global model. But that is no, we can fix it. We just have to manually do the connection. We have to model it, or we can use the connection library. In this case, I will use the connection library. We can then hit propose to get a complete connection or a suggestion for this topology, or we can simply do it one at a time. Okay, so let's connect the beam to the column, and IDEA StatiCa will suggest possible connections for this topology. So I will find something that suits this connection. This one is okay. Now I'll hit OK, and the operations is applied to the connection. So I see that I have some stiffeners on the web on both sides. They are clashing with this beam, but I can simply mark the stiffener and have the stiffeners only on one side. Now I have to connect this beam to the column. So I will right click on the beam, select connect to, and choose the web of the column. And in this case, we have a pinned connection with only shear. So I will choose this fin plate with some bolts and apply it to the connection. like so. And of course, we have to check the member, because this is a hinge. We have to change the forces in to bolts, like this. And we can move on with the code check. I hit calculate, and the program will code check the connection. So you see that it is quite simple to import a connection from your FEA software and then do the modeling of the connection in the application itself. You do not need a complete Tekla or Revit model to do this. So here we have it, the summary. It's the results are good, and again I can hit save, exit the connection, and move on to the next one. So the next topic is the connection library. I've touched on it a couple of times, but let's look at it more in detail and what it is. Let's say that you have a connection that you have used a lot of time modeling. You put on all of the operations like this. You set all the parameters, and you are happy with the connection. And let's say this is also a connection that is common to your work practice, and that you want to apply the operations to the next one. So you don't need to do it every time. In that case, you can save or publish these details to the connection library. The connection library you'll find up here. You can now publish this design. So you can either choose to put it in your personal connection design set or the company connection design set. In the personal, only you will have access to it with your user. If you put it in the company connection design set, all of the users with your commercial license in your company will be able to access it. I will publish it to my personal connection design set, and I can review it if I go to manage. Here I can see all of the connections in my design set. These are connections that I do not want to model each and every time when I have the same geometry. So now it's here. And let's say that next time you have the same geometry, or maybe your colleague has the same geometry, you want to apply the exact same operations and connection to this geometry. Now you can then hit propose, and you will get a selection of possible designs for this geometry. If you will get the predefined, the connections suggested by IDEA StatiCa. If I filter it out, I get the personal and the company design set. I want to use this one. This is the one that I previously modeled and published. I can hit OK and OK, and all of the operations is applied to this connection. And I can now start to apply the loads and run the code check. So this is the connection library built into the application itself. You can access the connection library either through the startup window for the application, or you can find it on the website. So this is a collection of over 400,000 connections. And basically you have to input the rough geometry of the connection. You can apply more members or remove them, and then select what cross-section they should be, the geometrical type, if it's ended or continuous, and possibly the angles and geometry. If we then hit search, we get all of the possible designs in the library that suits this geometry. So you can see that we have a lot of different possibilities, and you can then decide the one you want and then open it in the desktop. This requires that you are logged in with your user. And now the connection is opened in the desktop, and you can apply the loads and run it, or simply just inspect it, get some inspiration, and model the connection yourself. Now we have come to the last topic, concrete. We will mainly look at the detail application in the concrete today, but there are also some other applications to look at. It is the reinforced concrete section, the beam, the member, and the CHECKBOT. First, before I give a demo, let's look at the method on which the program is based upon. It will use the compatible stress field method. It's a fairly new method for design and assessment of concrete structures, particularly suited for so-called discontinuity regions, for which it overcomes the limitations of classical design tools. You can then do normal reinforced beam, of course. You can do cast in situ walls, deep beams, frame joints, openings, and coupling beams. It will do all the ULS and SLS checks required in the Eurocode. So you can see the results are very visual and well represented. And you can of course get everything in the tables and included in reports. There are also some tools for the precast engineers, prefabricated walls, corbels and brackets, non-standard beams. IDEA StatiCa detail is especially suited for this. Also, pre-stressed members, you can also include hanging supports in the details. Here also, all of the USLS and SLS checks are showed in a very nice way. There are also some tools for bridge engineers. You can do diaphragms, bridges, piles, pile caps, composite bridges or beams as well. Time-dependent analysis is also possible, and you see all of the results here as well. IDEA StatiCa also have a couple of cool tools to help you to assess where to put the reinforcement. So, for example, the linear analysis. It's a simple tool to get some understanding of where the compression and the tension is forming in your detail. And then you also have a more advanced tool called topology optimization. It will basically find the most effective volume and show you where the tension and compression is forming in your detail. So here is a couple of other examples of parts constructed or modeled in IDEA StatiCa detail. You can also do walls and panels. Some pictures of prefabricated walls and how they are assessed, beams of all topologies, and bridges, diaphragms, as I mentioned. So let's have a look at how the application works. So from the start menu, you go to concrete, and then you can open detail. The user interface is quite similar to the steel module, the connection module. You are presented with some templates you can start off from, or you can go with a blank project and create it from scratch. In this case, we will start with a wall. It has a window and a door, and we can then select the initial settings, like the concrete grade, the reinforcement, possibly the pre-stressing, the concrete cover, and then hit Create Project. Here we have our wall, and we will do some small changes to it and look at the results. So we can see that in the same fashion as the steel module, we have all of our members, our supports, loads, and operations on this tree here. So we also have the openings, that is the window, this is the door, and I can simply move the door if I want to do that. And then I will go to the supports. So keep in mind this is a template, and all of the supports, the members, the loads, the reinforcement, they are already there, and I can quickly change them if I want to do that. So in this case, I will delete the line support 3, and I will go to the loads. I see that I already have some line loads, trapezoidal loads here. I will stick with them and keep them. And then I have the load combinations. So here I have the ULS combination and then the two SLS combination, the quasi-permanent and the characteristic. I will not change them in this case, but I will move on to the reinforcement. So we have both group of bars, it's this reinforcement right here, and then the one on top of the door. I will run these tools before I start to change the reinforcement. I mentioned that we have the linear analysis tool. I will run it and we can get a kind of a quick picture of where the tension and the compression is forming in this wall. So this blue area is high probability of tension. I can run the more advanced tool, the topology optimization. So it's basically an algorithm that finds the most effective volume in this structure. And we can sort for 40%. And here we can see a much more clearer picture where we possibly should put more reinforcement. So I will elongate this bar going from the top of the door to the top of the window, and this diagonal incline bar down to this area here. So let's start with the incline bar. I will increase the top length to 2500, like so. And then the bars on top of the door, I will increase it to 1700, and now it goes from the top of the window to the top of the door. The reinforcement that goes outside of the wall, you don't need to worry about it. We have set a concrete cover of 30 millimeters, and it will automatically be cut here. There are also some cage around the opening. It is this operation here. I will stick with it. I don't need to do any changes to it. So let's run the code check and look at the results. So now the results are ready, and we get a summary of the code check here. We have the ULS checks of the concrete, reinforcement and anchorage, and then the SLS check with the stress limitation and the crack width. We then go to the check tab, and we can look at the results more in detail. So we can look at the strength, and then the stresses in the concrete, and strains, and possibly the plastic strains. And we can draw the mesh if you want to inspect how the mesh is generated. We can also look at the strength in the reinforcement, also the anchorage results, the stress limitations, long-term, short-term, and then the crack width, and then the different results within the crack width. And we have the tables below, and if we are happy with the results, we can then go to the report and generate it, and we can inspect the report. It has a picture of the loads, the reinforcement, summary of the results, and then in detail all of the results that is required to check in the Eurocode. You can of course have the report more detailed and export it to Word or PDF if you want to do that. Now we have gone through the steel module, the BIM links, the connection library, and the concrete. If you want to learn even more, you can go to the support center. You will find there a collection of webinars, theoretical background, and even training called Campus. We also arrange trainings, so just contact us if you are interested in that. Thank you for following. See you.